Okay, so our success criteria that we have for this one is that you can identify a continuous function from a graph, you can identify a continuous function from a real-life situation, and then you can find the domain and the range of a continuous function. So let's get started on this one. So the difference in a continuous versus a discrete function is that a continuous function is a solid line. So if I ask you to count all those points that were on this line, not these here, all the ones that were in here, there's no way you could count those points. There's just gazillions of points in there. The rule actually says in geometry, and you might remember that, it says between any 2 points, there's always another point. And so it's kind of like saying, when I look at this line, instead of thinking of it this way, thinking of it as just tons and tons and tons and tons of points that we did, to the point that there's so many lines that it looks solid. And some of you may have had art class in which you do the dot art, in which you put dots and dots and dots, but from a distance it looks like it's a solid picture. It's the same thing here. This here is made up of gazillions of dots. Okay, gazillion of dots. There's just tons and tons of dots. That's what makes it continuous. It is not countable. There's no way we could count all the dots. That makes it continuous. Okay? Now, domain and range of continuous functions, it's according to what the function is. So let's just talk about it. If I left this graph the way it was here, then my domain, in this case, I could say that my x value was, let's say, greater than or equal. We'll pretend that it kind of touches right here. Okay, just to make it easy for us. So my x values are going to go from roughly, well, let's just go. We'll say negative 1.25. Okay, and they go all the way. So my x's, let me make this a little bit darker here so you can see it. Actually, maybe see if I can make this or not. So we could look at it as a box, okay? How I showed you how to do that. So if you could think of it as a box, okay? I can't really make a box here on this one, but if you think of it as a box, then maybe that will help. And so it goes from 1.25 on my x's. Let me get a different color though here. Okay, so all my x's that I see are going from about right here to about right there. So I'm going to say it's going from 1.25 to maybe 3.75. Okay, we'll do that. So that would be my x's. That's the only x's I graphed. You don't see x's over here or any graph over here. My range now is going to go from all the way up here at the top. Okay, so my range is going from here to there. Okay, all of those y values are graphed. And so my range values are going roughly from 6 all the way down to a -6, we'll say. Okay, so those would be my domain and my range values. So when I do domain and range for continuous functions, I need to do a couple of different things. One is I could write them as inequalities. Okay, and the other is that we could write them in what we call that interval notation. And for some of you guys, I've already showed you that, and we will definitely do more of that. So where discrete graphs were just a set of points, continuous functions, you either have to write an inequality or interval notation for it. So we could do the same thing for this one here. So our domain, our x values on this one, looks to me like it's going from about right here. Again, that color does not show up. So maybe for about right here, we'll call it maybe 1.5. That's kind of hard to see, all the way over to here. Okay, so this would be my x values. So I would say x goes between -1.5 and let's say 4.75. Okay, so those are my x's. My y values on there now are going to go from, again, the top all the way to the bottom on here. So my range values, my y, and do put it y there because that's what we're talking about, would go everywhere all the way from maybe 5.5, that being my highest, to a negative 6.25 maybe. Okay. So again, when I look at it, you can definitely see a difference between the continuous and discrete, especially with how we write our domain and range. So here's an example of domain and range with continuous. So example might be pounds and costs. So that means, like if I go buy apples, let's say this is apples, okay, apple. Okay, so we could have different weights on there. The apples is probably not a good one. Let's do something else. How about if we're just doing a chemical? Okay, maybe we're in the lab and we're buying chemicals, or you're buying screws. They're by the pound on that. So you would have the number of pounds that you buy versus the cost, or maybe seeds or feed or whatever. And so because we could have smaller and smaller and smaller amounts of it, little grains of it per se, we're not going to say 1 pound, 2 pounds, 3 pounds. That's why I changed that. But things like that you weigh out a lot of times, there's all these little bitty points that are in there. So this one would be another one, time and volume. So that might be if you're like running water and you want to know how much volume you've got in a container. So because seconds can go to such a small numbers, we could go milliseconds and so forth. We could keep getting smaller and smaller in our values. Okay. Again, so when we go to do our domain and range, on here, our pounds, our x values in this case would all go over all the way from 0. So it's not going to go below 0. And a lot of your real life situations, especially with continuous functions, they actually don't have negative values. So really my x here would be everything greater than or equal to 0. And in theory, unless they specifically said it's stopping, it's going to keep going on and on. Your range here is going to be the same thing. It's going to be everything greater than or equal to 0, because again, if it kept going on. Now, if they specifically stopped it and said, okay, I'm going to stop it right here, so like, then maybe you might have an endpoint to it. Okay, same way for here. Okay, so let's look at this graph here. Now, this graph actually goes from here to here. So that's what we're going to look at in terms of our domain and our range. So our domain here, x values would go from 0 over to, I think that's 10. So less than or equal to 10, greater than or equal to 0, okay, because we're talking across here. See, this one didn't really have an endpoint. We could have said it stopped there, but I put an arrow on it, okay. Everybody see I put that arrow on there. Range here from, that's going from about 10 to 1. And then again, we would have that interval in there. So think of our intervals that we did with the graphing of our inequalities, and especially our and values and so forth. That's kind of what we're going to see here, that same kind of thing. And again, I'll show you more of the interval notation as we start doing more. Okay, let's see what we have. Here's a real life example. So it says Amanda walks at an average speed of 3.5 miles per hour. Now that's her average speed. D of x gives the distance in miles. Amanda walks in x hours. And so really what we're having here is hours and distance. Okay. If we wanted to go ahead and write our function, d of x is 3.5. And again, that's miles per hour times x hours. So 3.5x, but if you look at the labels, that also helps you to write your equation, okay, because hours and hours cancel and it gives you distance miles, okay, and we'll talk more about those kind of problems. But if we go, in this case, 0 would be 0, But if she goes 1 mile, she's going to have gone 3.5. If she goes 2 miles, she'll have gone 2 hours, sorry, not miles. She'll have gone 7 miles. And 3, she would have gone, 10.5. Okay? And so when I go to my graph, though, I'm going to have the number of hours and the distance. Okay? So we're going to have 0, 1, 2, 3, 4, so forth. And again, we're going to have, I'm going to go ahead and go up with these evens. Here makes it a little bit easier. And that would be 14 there. And so 0, 0, okay, 1, 3.5, 2, 7, 3, 10.5, okay, 4 would be so forth. But here's the thing about it. Nobody says that she had to go a whole hour. Maybe she only went a half a mile or a half an hour or a mile, an hour and a half, so forth. And that's why we can draw this, okay? Because we don't know that she went a full hour. She could have only gone 15 minutes, or she could have gone, whatever. And so this is just her average of how fast she is. So, if she went 2.5 hours, we could predict how far she would make it. If she went, 3.5, we could predict how far. And so again, that's why we connect the dots and it becomes a solid line. And you've probably had some of this talk maybe in your science classes and so forth, where you're collecting data, when to know when to and when to not. Okay, so this one has a cable. It has a 3/8 inch in diameter and weighs 0.24 pounds per foot. Again, it is the same thing, the weight, and it is 0.25 pounds per foot, okay, 4x feet on there. So when we come to do this, this would be feet. This would be, 2.4 pounds per foot. So, and then how much it weighs. They also do cost this way. So if it happened to be 1 foot, it would weigh, that's pounds. It looks like a 16, but it's pounds. Put an S there. It would weigh 0.24. If it, can't read that. If it was 2 foot long, then it would weigh 0.48. And if it was 3 foot, then it would weigh, that'd be 372. And then if it was 4, 96, so forth. Okay? And so, but when I go to graph it, okay, and I'm going to again go up by 0.24, makes more sense than to try to estimate the value. So don't forget, you're in control. The key is that your distance between each of these is exactly the same. So again, 0, 0, 1.24, 2.48, 3.72, so forth. But the same way on there, it's per foot. And nobody says you have to buy a full foot. Maybe you want to go and you want to say, hey, I only want 3 inches. Okay, they're going to cut 3 inches off. So again, there would be our graph. Okay, and our equation. Okay, so that was kind of a quick examples of where you're going to see the difference between continuous and discrete. Hopefully you can pick those all out as we start doing applications of those.